class, welcome. This is Puan Anita teaching for Physics Semester 2. Today's learning outcome will be to derive the formula for the force between two parallel current carrying conductors. Force between two current carrying conductors. Okay, I have two long parallel current carrying conductors, which I'm going to draw here. Two long parallel current carrying conductors. Okay, wire X and wire Y, right, carrying a current I1. This is I1 in the same direction. This is I2 in a vacuum. Okay, in a vacuum. Okay, and separated by a distance D. Okay, when current I1 flows in the wire X, okay, so right, so when the current I1 flows in the wire X, there is a magnetic field produced around the wire X, and we know this is a straight wire. Let's look at wire X here, straight wire, and we know that the pattern of the magnetic field will be a concentric circle. So I'm going to draw a concentric circle here. Okay, I'm just going to roughly draw your class. Okay, just going to roughly draw that. Okay, alright, so I'm going to draw with this. Okay, there's a concentric circle. Okay, so it's a magnetic field around wire X, and magnetic field is a vector. It has a direction, so I use my right hand grip rule. So this is a straight wire. I grip my wire. Okay, so the thumb will point to the direction of the current, and then the fingers will point to the direction of the magnetic field. So I get my direction of the magnetic field in this direction. Okay, all right. Okay, so now we want to find the B at this position here. The B at this position here. Okay, which is a distance D from I1. Okay, so the B at this position here, before that, I'm going to label the B as B1. Label the B as B1. So the B at position, okay, at distance D will be B equals to mu naught I1 over 2 pi D. So you see I'm using a straight wire B. B for a straight wire. Okay, so B at this position here 1. So B1 equals to mu naught I1 over 2 pi D. Okay, the B1 here. Alright, so at position here, at position or distance D from the wire X, there is a wire Y in the magnetic field of B1. Okay, so what will happen to wire Y? Wire Y will experience a force. So you see there's a magnetic field. A wire Y is put into the magnetic field of B1. So wire Y will experience a force. Okay, will experience a force, which is F2. I will let you know why the direction is such as F2. Okay, so F2 is equals to BIL. Correct? The general formula for F2. So in this position, F2 is inside who? Okay, F2 is caused by who? By magnetic field of B1, and here the current is I2L. Okay, alright. So we get F2 equals to BI I2L. Okay. Now let's look at the next one. Okay, let's look, now we separate X. Now let's look just at Y. Okay, just look at Y. Okay, Y is carrying a current. Therefore, Y will have a magnetic field around it. So if I draw, it will look like a concentric circle pattern. Okay, I'm just going to draw roughly here. Again, just roughly here I'm going to draw. So the direction of the magnetic field pattern, this will be the direction of the current, the magnetic field. So it will be like this. Okay, alright. Okay, and the field, I'm going to label it as B2. Okay, so now if you look at this picture here, the B at a distance, B2 at a distance D from the wire Y will be B2 will be mu naught I2 divided by 2 pi D. Okay, alright, and then this is the field of B2. Suddenly X is inside the field of B2. So what will happen to X? X will be exerted by a force. X will be experiencing a force, which is we're going to label it as F1. Okay, so F1 equals to BIL. So F1 is caused by the magnetic field of B2. Current here I1 L. Okay, alright. Okay, so we already got this. Now let's look at this now. So F2 equals to B1 I2L. We substitute inside here. So we get F2 equals to mu naught I1 I2 over 2 pi dl. Okay, we substitute this one inside B1. Okay, alright. Then we also substitute this one inside here. Okay, so we get the formula F1 is equals to mu naught I1 I2 L over 2 pi D. Okay, alright. Now, next. Now, comparing both the equation, number 1 and number 2. Okay, so we can say the force on the wire X and Y are the same magnitude. F and F force, these two force are the same magnitude. F2 and F1 are the same magnitude, but they act in opposite direction. Okay, why opposite direction? I will explain to you all later in the next video. Okay, alright. So we can say that the pair of forces is an example of action and reaction in Newton's third law of motion. So F1 is equals to F2. So therefore is equals to mu naught I1 I2 L over 2 pi D. Okay, so another way we can say it is force per unit length. Force per unit length. Okay, F over L is equals to force per unit length equals to mu naught I1 I2 over 2 pi D. Okay, so this is the force between two current carrying conductors. Okay, so what are we doing now, class? We are now finding the force between two current carrying conductors. Force is a vector. Okay, force is a vector. So now in this video, we are finding the magnitude of the force. The next video, we are going to look at the direction of the force. Okay, alright. Okay, thank you.
Okay, it is said that when two conductors are carrying current in the same direction, then there's a force of attraction between the two wires. Then it's also a fact that if the two conductors are carrying current in the opposite direction, there is a force of repulsion. Now let's see how that happens in the next video.
I'm going going to look at the force between two current carrying conductors. We are going to talk about the direction of the force. So you see here, I have two conductor carrying current where the direction of the current is out of the page. Okay. So now what I do is, this is X, this is Y. They are carrying current I1, I2 in the same direction. Okay. So I'm going to talk about the direction here. So the first thing, this is the conductor carrying current. So I draw first the magnetic field around it. The pattern is in concentric circle. Okay, so I use my right hand grip rule, so the direction I will get like this. Okay, alright. Lari already. Same pula. Okay, anyway, the next one I draw, it will also be in this concentric circle. Oh, okay. Okay, so the pattern of the direction of the magnetic field will be also in this direction. Okay, in this direction. Okay, so what happens here, class? In this place here, you will realize that here the B will cut out. B will cancel. Okay, why? Because this is B1, this is B2. Okay, so you see that the direction of the B is opposing each other. So the resultant B, the total resultant B will be B1 minus with B2, because they are same value, right? So the total resultant B in the center will be 0. So here will be weak. The B is weak or don't have B. Okay, weaker B. Okay, but here at the end here is B1 and here is B2. So the B here is stronger B, because this one is B1, this one is B2, so here will be stronger B. Here also will be stronger B. Okay, so a force will start to act from the stronger region to the weaker. Okay, a force will start to act from the stronger B to the weaker B. So here is strong, here is weak, so the force will start to act. Strong to weak, so a force will start to act. So that is the reason why the force will be an attraction force. So what they say is that if the wire are in the same direction, then there's a force of attraction between the two wires. Okay, let's look at if the wires are carrying a current in the opposite direction. Okay, this one current in the same direction. So say for example, this is a dot, this is an X. Okay, alright, so I draw the magnetic concentric circles here, the magnetic field pattern here also I draw. Okay, so the direction will be in this direction, and then here I use it here, it will be this side. Okay, so in this case, in the center here, you realize that the B, this is B1 and this is B2. Okay, so you realize they are in the same direction, so their pattern of their field will be something like this, because they are same direction, so their resultant will be, total resultant B will be B1 plus with B2. Okay, their B resultant, so here the B is stronger. Okay, here is B1, here is B2. So here is weak B, here is a weak B. So the direction of the force will be from the stronger to the weaker. So the force will act from the stronger field to the weaker field. That's what I'm trying to say. So that is the reason, from here to here, so the direction of the force will be in this direction. Okay, so that is the reason why if the current are in the opposite direction, it is a repulsion between the force is a repulsion force. Repel. Okay, all right.
1 ampere, or sometimes is often shortened to amp, is the SI unit of electric current. It's one of the 7 SI basic units. It is named after Andrea-Marie Ampere, a French mathematician and physicist. The definition of 1 ampere is the value of steady current in two straight parallel conductors. We have two straight parallel conductors, infinite length, negligible circular cross section, separated by a distance of 1 meter in vacuum, producing a force of 2 times 10 to the power of negative 7 Newton per meter length. That means force per meter length on the conductor. Now, after 2019, the definition of 1 ampere has been redefined.